I'll get started. So today I'm talking about linear and cyclic codes, which is just sort of a way to formalize Hamming codes that we've talked about in the past. And we'll talk about another type of code that allows us to do some cool other types of error detection. So just as a recap, the basic problem that we're dealing with is we're trying to send messages between people, and those messages are going to get corrupted. So how are we going to detect that those errors happen? How do we correct them? And we want to send a message that minimizes the redundancy we use to correct and detect errors. And another question is, what if we only care about certain types of errors? When we're talking about different types of forms of communications, the pattern that errors have tends to become relevant, and that's going to influence the last type of cyclic code that we're going to talk about. So first up, we're going to formalize Hamming codes a little bit. So I don't know if you were here at Sam's Hamming code meeting, but just to do a reminder of what Hamming codes are like, we're sending a 15-bit message, of which only 11 bits actually represent the message we're talking about. In this example, we've sent a message, and this 0-bit has been, it used to be a 1, and we flipped it to a 0. And what we can do is we can look at different segments of the matrix, and this is sort of a recap of the meeting from 2 weeks ago. We can look at different segments of this matrix, this sort of grid that we've got, and check the parity bit. So this one, the parity is even, this one, the parity is even, this one, the parity is odd, so we know there's an error somewhere in this half. Here, the parity is odd, so we know there's an error not only in this half, but also in this row. You know, that's where the error is. And then this one's fine. So we can deduce that the error is happening right here, because there's no error there. It's just a recap of a few weeks ago. That's how Hamming codes work. We're going to formalize them today. Yeah.
I saw this problem like a couple weeks ago. Couldn't it still be the bottom row, third column?
This column or this?
Yeah, that one. Couldn't that one be a 0?
So we know that we know from here that the error is going to be in this
because
one.
of the far right one. It can't be.
Oh, is there a
Okay, good.
Oh, you are right. Actually, that should be.
No, this is fine. It's fine now.
It's fine now. Okay.
Oh yeah, okay, yeah. There's 4 things. Yeah, so
Right.
got it. Okay.
Okay, good.
I just copied it from the previous meeting. Yeah. Cool. So that's just a recap of what we did before. But before we go back to Hamming codes, we're going to talk about what it really means to correct an error. So we're going to deal with a simpler type of code, which is just the best 2 out of 3 code, where for a message M, we're going to take every single bit that we get, and we're going to repeat it 3 times. So the valid words we have in this code space are just 3 zeros and 3 ones, right? But the language contains 2 to 3 words. It contains 8 words. So there's a lot more room for us to work with. We've raised the dimension of our message space. You can actually visualize this, where initially the messages we're sending are either a bit of 0 or a bit of 1. If you flip a bit, I mean, you can't figure out that anything's gone wrong. Both those are valid. Versus once we've encoded this in this best 2 out of 3 method, you've got a much larger space to work with dimensionally. If you flip a bit, you know how to get from somewhere, back to where you were. And another thing we could do is if we talked about Hamming distances when Anakin gave his meeting, and I think Sam really briefly covered them. You can sort of see the Hamming distance here. The shortest path from this all zeros to all ones is going to be a path of 3, which is the Hamming distance. But we'll formalize that as well a little bit more as we talk about it. But I hope this makes sense, where it's just one way to think about codes is we're taking a message that's in a lower dimensional space and increasing the dimension that we're working in, so there's more room for us to make errors. Generally, when we talk about codes, we're going to talk about an n, k code, and sometimes people talk about an n, k, d code. An n, k code means we're sending n bits with a k-bit message. So the Hamming code that we talked about previously was a 1511 code, where we're sending 11 bits of messages with 4 bits of redundant information to help us correct errors. We're going to talk about a 7.4 code right now because we're going to be making some matrices and they'll get really big if we do 1511. But so we're talking about having 7.4 codes. We're sending 7-bit messages, of which 4 of those are the actual message we're sending, and 3 are just extra information. Yeah, 3 additional bits of information to search over these bits, just like the other Hamming example. So you can think about the Hamming 7.4 code just like the Hamming 1511 code. It's a little harder to visualize, and that's why I didn't draw it, because I thought it'd be more confusing. But now you've got 8 bits, and you're sort of partitioning them, and you're like sort of binary searching over them. But we're mathematicians and we don't like talking about binary search. We like talking about actual math. So specifically, you can do something like this, and we'll talk about how you actually come up with these in a little bit. You can XOR the first, second, and fourth bit, or 0th, second, third bit, first, second, and third bit, all mod 2. And each of those, if you try and visualize in your head, those little awkward, it's like a 4x2. We'll cover every single possibility, and we'll be able to recover a message using this Hamming-4 code. You don't have to work it out; you just have to believe me. But it's true. Well, actually, we'll see why this is true pretty soon, and where you come up with these. But does that make sense so far? And you can work it out if you want to. Okay, so one of the neat things about this, though, is that these are linear equations, all mod 2, and linear equations imply that we've got linear algebra. So I guess what that sort of means is, can we make a matrix G such that when we take our message and multiply it by that matrix, we get that encoded ciphertext with those additional 3, bits. Code text, not ciphertext. We can. The matrix looks something like this, which is very similar to what the equation we saw earlier. We've got the identity in the first 4 columns because we just want to copy over the first 4 bits of the message. And then down here, we're taking the 0th bit, the first bit, and the 4th bit, or 3rd bit. Same thing over here, same thing over here. We just turned these equations that we've got into a matrix. So far, so good. What's nice about this, though, is now we've got linear algebra, and that gives us a lot of nice properties, right? We've just said that the Hamming code that we talked about, we can talk about as a matrix, which means that any things we do with matrices, we can also do with Hamming codes, mainly linearity. So with a Hamming code, and with any code word, you can sort of any code you can make by doing this matrix technique, we know that any 2 messages, when we sum them together, are another valid message because our message space is, every binary string of some length. But that also means is that the sum of any code word is also a code word, because if you multiply something with a matrix, you're going to get, like x plus a times the matrix, the same as x times the matrix plus a times the matrix. We're going to prove some interesting properties using the fact that these are linear. So earlier, I think one of the first meetings of the semester, we talked about the Hamming distance and the minimum distance of a code space, which is the minimum difference between any 2 code words. So if you write this delta xy as the number of positions where the ith character of one of your code words is not equal to the other character of that of a different code word, right? That's like the distance between 2 code words. It's just anytime the bit flips. Then we could say that the min over any 2 code words of our language, the min of this delta over any 2 code words, is the minimum distance, right? Like that's what we're talking about. But when you've got 2 code words, we can shift them over, right? If you think back to that weird sort of cube diagram we had, if you want to find the distance between 2 code words and you shift them both down, the distance is still the same, right? So we can subtract C1 from both of these because it's linear, and the distance hasn't changed. Does that make sense? We've just subtracted some common word from both of them. So now the minimum distance is really just the min between the 0 code word and C2 minus C1. But once again, C2 minus C1 is also just going to be another code word, right? Because they're linear. So this is just the min over any code word. And that's just the minimum Hamming weight of any other code words. So the minimum distance is, you can find just by looking at all of the code words in your language and counting how many ones they've got. And the one with the smallest ones is the minimum distance that you can have with that code word, with that code space. Does that make sense so far? Cool. Okay. Now we want to do something else. We want to be doing parity checking, but with linear algebra, as opposed to just like sort of doing it by hand. So we want to find a matrix H such that HC transpose is 0, where C is some code word in our space. Why do we want to do that? The reason we want to do that is because linearity gives us really nice properties. If we introduce an error into our code, so rather than sending over our code, we're sending over our code plus some error. If HC transpose is 0, then when we multiply H by that, the C plus E term, when you get HC transpose plus HE transpose, C transpose just goes away. It's 0. So what does that leave us? What is HET when you've introduced an error. EFT is supposed to just a 1-bit error. So E transposed is going to be a unit vector, right? Just a single bit set. So it gives us a column in H that's associated with the error. And what's nice about that is we know which column has been flipped, right? We know which column introduced the error, so we know which column the message has been flipped. We can do a lookup and figure out which bit got flipped. So now using matrices, we can correct errors. This HEFT, HE transpose, we call the syndrome vector. Just if you're like reading papers or something, you see people talking about syndromes. That's HE transpose. So I'm not going to do this because it's not super useful, but I'll leave you guys a few seconds to do this. We know that HE transpose is equal to 0. You can sort of think about that, right? HC transpose is 0, and we know that MG is C. So if you do some math, you're going to get that HE transpose is 0. And then knowing that, you can deduce what H is, which is just the list of our parity bits, and then the identity. If you want to work that out for a few seconds, that's fine. But I can also just move on. It is just basic like linear algebra manipulation, and then it's sort of just staring at it until you see that this is how things line up so that everything goes to 0. Make sense so far? All right. So Hamming codes in a general sense, because we've talked about 1511, we talked about 7.4, and we had these weird parity bits that just kind of came out of nowhere. One way you could come up with those is you could do, you can make a grid and you can like split it in halves and do like that weird binary search that we did with Hamming codes. Another way is to realize that Hamming codes, by definition, are a code where the parity check matrix has columns with every single number represented in binary. We'll talk about why that leads to Hamming codes. Okay, so to make a Hamming code for higher dimensions, what we'll do is we'll create a matrix that has, every single number, so except for zeros. So 0, 0, 0, 1, 0, 0, 1, 0, so on, all the way to 1, 1, 1, 1. And then we'll reorder it so that it fits this parity matrix we got earlier, where the identity is at the end. And that'll give us a parity check matrix, and also it'll give us P. So this is a vector, this is a matrix of just that. It's every single number, 1, 0, 0, 0, 0, 1, right? Then I'm going to move these over so that we have the identity over here. And now each of these represent the parity check matrix. So we'll be, our first parity bit will be the, M1 plus M2 plus M4 plus M5, et cetera, et cetera, et cetera. Why does this work? Why does this actually allow us to, ensure that we're covering every single possible error? The way that I like to think about it is that every single row guarantees that we cover one bit of the message, right? So here we've got a row that covers every single row, make sure that like this thing covers the first bit of the message. If you sort of transpose it, this thing covers the first bit of the message. Every single one of these is covering one bit of, if you divide the message up into a grid, it's covering like one corner of the grid. And then every single, like the second row is doing the same thing, but with like halves, etc. It's a little hard to visualize. I couldn't find any good visualizations and I couldn't make one myself. But this idea is how, Hamming sort of came about it. Is he first came up with this realization, this idea of codes sort of already existed. He came up with this realization that if you make a parity check matrix with every single number and you leave out the identity because that doesn't give you any useful information, what's left is going to be enough to cover, it's enough to undo, one by one, if that makes sense. It's a little tricky to visualize. I'll let that sit for a little bit. But we could do this with any dimensions now. Now that we've got sort of an algorithm to create, like those parity check bits for any type of Hamming code, we could increase the dimension of this matrix, get many more elements, repeat.
I guess my only question is, you're saying moving the previous columns around. Does it matter how we move the previous columns around? Or could any permutation of these columns?
Any permutation of these columns will work, as long as you maintain the column ordering, right? So this one column represents like a binary number, and you can think about that as indexing into that grid. And we do, so we're indexing into every part of the grid except for these things, which if you do the grid visualization that Sam did, end up being like the locations of the parity check bits. Each of these is one index into that grid. And then this is like we're summing over them in such a way that we're hitting exactly the various halves that we want to generate what we need. So yeah, the order doesn't matter as long as they're all there. Okay, so that was a small covering of like linear codes, which is just this idea of we're going to take a message and we're going to multiply it by a matrix to get the code word. Hamming codes are a type of linear code, but you can make linear codes, with just any generator matrix that works like that, right? Not all of them are useful. Hamming codes tend to be the most useful ones. We're going to talk about a different type of code that is both a linear code and also a little bit more called the cyclic code. So why? One, because we can do some more math. We'll start talking about like polynomials and stuff, and that's always fun. But also, Hamming codes, all Hamming codes, have a minimum distance of 3. So you can only correct up to 1 bit of error, which isn't super useful in the real world. Unfortunately, Hamming codes are also quote unquote perfect. So for the size of the Hamming code that you've got and the rate that you've got, that is the most amount of errors you can correct. So that leaves us with a little bit of a problem. We usually have more than 1 bit of error in a message. But at least over the network, which is where cyclic codes came in, most errors happen in bursts. So you're sending along a message, and then maybe like the power drops, something happens, and 5 of your bits are corrupted, and the rest of your bits are fine. Right? Most errors don't happen randomly throughout the message. They tend to happen in chunks called bursts of errors. Previously, we're working under the constraint of we want to correct an error that can happen anywhere. And doing that really restricts us because, that's just a hard problem to do, right? That's information theory tells us that's very difficult to do without tons of extra information. With this constraint, though, we're looking to fix, maybe 1-bit errors in various places, but also any sequence of errors. We can do a lot more things. So cyclic codes are pretty self-explanatory. They are cyclic. So C is a cyclic code. If you write it as like a vector, and it's got n elements, then if this vector is in C, then all of its elements shifted to the right are also in C. That is the only property that cyclic codes have. That's not really useful though, because you can imagine an example, and maybe I should have made one, where you've got a cyclic code, but they're not linear. Like if you take a cyclic code, you add 2 of them together, and you don't get a code that's still in your code space. So usually when we talk about cyclic codes, most people are talking about linear cyclic codes. And oftentimes you'll see people talking about cyclic codes, and they really just mean linear cyclic codes. Because cyclic codes by themselves, kind of useless. So linear and cyclic. So an example code space of this is all zeros, 1 0 0 1 0 0. Then we shift that to the right once. We shift that to the right once. And then it's inverse. 1 1 0 1 1 0 0 1 1 0 1 1. These are all just shifts, and then all ones. We can look at this and convince ourselves that this is linear. If you add 1 0 1, if you add these two together, you get this one. You add these two together, you get all ones, etc. Right? Like you can add any one of these together, get a different one. This is all mod 2. So if you add like all ones to something like this, it's like inverting the bits. This is all mod 2. But we can add anything together and get another thing in it. And any code word in here, if we shift it, we get a valid code word. This isn't something with linearity that doesn't apply here that I was a little bit confused by when I was looking at it first, is with linearity, every message is made up as the sum of 2 messages. You can write any message as the sum of 2 messages. With linear cyclic codes, you can't write any message as the shift of another message. You can any code as the shift of another code. You can take a code, shift it, and get a valid code, but that doesn't imply the other direction. Yeah, every sum of a code word is code word, and then shifting any of these is going to give you a valid code word. Cool. So we can think about code words as a sequence, and then we can create a generating function for these sequences. So the way we do that is we take the first bit and we multiply that by x to the 0. We take the second bit and multiply that by x to the 1, so on and so forth. If you look at the first code word we were looking at earlier, 1 0 0 1 0 0, you get this polynomial, once you get rid of all the zeros, you can represent that as 1 plus x cubed, and that's a unique representation, right? Because we're working under, every single additional bit is raising the power. You can't do like additions and subtractions and chain of powers and things like that. So these are all unique. And they have a lot of really nice properties, right? So we took Hammond codes, we turned them into matrices, we got linearity out of them. Polynomials are also linear, right? You can add two polynomials to get a polynomial. But also polynomials are they, is there a bijection from polynomials to the integers? Probably is, but you can do a lot of really cool things with them. They behave a lot like
Cardinality
integers.
wise, yes, homomorphically no.
Homomorphically, no. Okay, so they're not homomorphic to integers, but they're pretty close to integers. Specifically, we can do polynomial division, which lets us do modular arithmetic. So we can talk about doing, like division over polynomials. And I actually don't think I write this ever again in the slides, but oftentimes you'll see people write z sub 2 x. This is read as c sub 2 adjoin x. That's what the thing is. And that just means that we're talking about polynomials where the coefficients are zeros and ones. So yeah, let's try and do a division. We're going to divide x cubed plus x squared plus 1 by x squared plus 1. What does this give us? Does anybody want to try? If you remember synthetic division from way back in like algebra 2, don't worry, we won't be doing it anymore. Still an example. If you don't, another sort of, the way that I like to think about it, the way that makes this easy, especially for the rest of the examples in the slide, is when we're dividing x squared plus 1, we're dividing by x squared plus 1. That's, oh wait, actually we can't do that yet because we're not taking any mods. Anyway, I'm not going to bother you with synthetic division. You get q is x plus 1 and r is equal to negative x or just x. So that is, yeah, that's fine. Okay. And if we, so x cubed plus x squared plus 1 mod x squared plus 1 is just going to be x, right? Because that's what's left over. That's the remainder, that's the definition of modulo. And the quotient is x plus 1. We're not really going to care about the quotient too much in this slides. But does that make sense? We can do polynomial division. We're going to get a quotient and a remainder, and that quotient and that remainder is the same thing as what we do if we were taking, modular arithmetic. I think that should be q times x squared plus 1. That's why I was confused. Sorry. Also, yeah. So for the rest of the slides, and just in general, when we're talking about cyclic codes, we're going to be working with polynomials in the form f of x plus 1. Where f of x is just, some function. So f of x plus 1 acts like 0 because we're doing modulo. So you can think of it as substituting every occurrence of f of x with 1. If we did that here to get the remainder, we'd replace this x squared with 1. 1 plus 1 would cancel out to 0 because we're mod 2 still. And then we'd replace the x squared inside of the x cubed with 1. So we're left with 1x, which is the remainder. That's a usually nice way to do these problems quickly, because we're almost always going to be working with stuff that's mod something plus or minus 1. Okay. So cyclic codes fall out of polynomials pretty naturally. If we go back to one of our initial code words, which we represent as 1 plus x cubed, the maximum degree of a polynomial in our code space is x to the 5, right? So we've got 6 bits, but one of them is x to the 0. So x to the 5 is the maximum degree. If we take all of our code words mod x to the 6 plus 1, why are we doing x to the 6 plus 1? Because then anytime we get x to the 6, it just turns back around into 1. Then multiplying by x gives us x plus x to the 4, which is our code word shifted right. We can continue to do this. Multiplied by x squared, you get x squared plus x to the 5th, which is our polynomial shifted 1 to the right. And if we did it again, we multiplied by x cubed, we'd get x cubed plus x to the 6th, but that x to the 6th would turn into 1, and we'd get our original polynomial back. Right? So in general, if some polynomial c of x is in our code space, x times c of x is also going to be in that code space, because x times c of x is just shifting it to the right by 1. But our code words are also linear. So if c of x is in our code space, then c of x plus c of x is also going to be in our code space. And so since x to the n c of x is in our code space, and c of x plus c of x is in our code space, we can write any polynomial out here and multiply it by an element in our code space, and that is also going to be an element in our code space. So you don't have to just use elements in the code space. You can just write any polynomial you want, multiply it by something in the code space, and you'll get a valid code space. So if we can write one of the valid code words in our code space, we can use that one code word to generate the rest. I've used generate a lot, and they all kind of mean slightly different things. I don't know. That's just the terminology that people use. So if we've got 1, 0, 0, 1, 0, 0, which is 1 plus x cubed, can we generate all the other code spaces, code words, by doing some polynomial multiplication mod x to the 6 plus 1? We can. 0, the 0 code word is just 0 times g times x. 1 plus x cubed, which is what we started with, is just 1 times g to x. These are just the shifts, right? We've already seen these. These make sense so far. But we can also make the other ones. 1 plus x cubed plus x to the 4th, which is like, 1, 1, 1, 0, 1, 1, is just 1 plus x times that initial generator. This one. Do the same thing for this other one, do the same thing for this other one, do the same thing for this big, all ones. So we call this polynomial the generator polynomial because it can generate any single, element in the code space just from knowing it. Is it unique? Any ideas? This x plus x to the 4th is just our initial polynomial but shifted to the right by 1, right? If you multiply it by like x to the 7th, that's sort of like shifting to the left. To x to the 7th? I think so. It's this. Yeah, x to the 7th. No, x to the 5th. Because 6 goes to 1.
Oh, right.
Yeah, x to the 5th. Multiplying by x to the 5th is shifting to the left by 1. So we could have picked this one. And we could have picked this one if we did, x to the 4th. And then we adjusted all of these appropriately. So it's not unique. We could have done that with any of the first 3 polynomials. Probably could have done it with any of the other 3. But in general, we call the polynomial in our code space with the lowest degree the generator polynomial, just because it's nice to work with. It's got the lowest degree, etc. So it's technically not unique, but when people talk about the generator polynomial, they're talking about the polynomial with the lowest degree because it's nice to get things in name. So we can encode a message by doing what we just did, right? If our message is, if we've got a generator polynomial with degree r, and we want to send, k bits of messages, then we're going to need to, we can encode message size k using a generator polynomial with degree n minus k. So the idea here is if you're trying to send, say, a 6-bit message, and our generator polynomial is 1 plus x cubed, like we were talking about earlier, we can send a message of, if you're trying to send a 3-bit message, and your generator polynomial is 1 plus x cubed for 1 through 6, then the degree of your generator polynomial is going to be n minus k. You can just multiply the message by the generator, if that makes sense. Because we want our generator to raise our message to the highest power, but not higher enough so that it wraps around, if that makes sense. That's where that n minus k comes from. But we can send messages, and then how do we get a message back once we've done this? Once you've done this multiplication, to get the message back, you can just do the polynomial division, right? You can divide the code word by g of x, and if there have been no errors, you can get the message back as a polynomial, which you then convert into the 1s and 0s like we did. Since these are linear codes, we can make that generator matrix we talked about that we did for Hamming codes. There's nothing really special about it. So you can think about how to form them. They do have some nice properties related to the generator polynomial, but there's nothing we gain from them. So I'm gonna leave that to you guys to think about. Yeah, so if we've got c of x equal to m of x times g of x, this is our code word, this is the initial message. We can get the message back just by dividing. That's great. If there was an error though, we'll have a remainder. So for single bit errors, just like we did for linear codes, if you remember, we had that syndrome vector, we looked it back up in the matrix to figure out which bit that error happened in, and then we can figure out what happened. Here we can do the same thing. It's a little bit more complicated. If you see this in hardware, this is often done in hardware because shifting things around is really fast. they'll have lookup tables mapping polynomials to like polynomial remainders to which bit the error happened in. But the bigger and bigger your bit size gets, the more annoying that happens. And this is no better than having codes, right? We've talked about all this, and all we can detect is 1-bit errors. And we need like a massive lookup table associated with it. It's not as fun. So using cyclic codes, though, we can talk about something called CRC, or cyclic redundancy checks, which is the form of, like redundancy check done with like most networking. In TCP and UDP, when you're sending things over the network at the data layer and at the network layer, at the transport layer, CRC is used to detect errors, correct messages, things like that. Talk a little bit about why. But here's the idea, and stick with me for a little bit, and then we'll try to work it backwards. We're going to take our message X, we're going to multiply it by X to the R. You can think of that as just shifting our message to the right by R, bits. Where R is the degree of the generator polynomial. And then we'll divide that by our generator, G of X. So we'll end up with X to the R M of X equals some quotient times G of X plus some remainder times G of X. Just some remainder, right? It's just polynomial division. Under Z2, which is what we've been working in this whole time, addition and subtraction are the same thing. So we can think about Q of X times G of X is just the same thing as X to the R times M to the X times M of X plus the remainder, right? So we've done division, and now we just add a remainder back. So you can think about this as we've gotten we took our message M, we padded it with a bunch of zeros, we divided that by the generator, and whatever remainder we got, we filled those zeros in with. That's where we're at so far. If we transmit this message, this will be divisible by G of X. So we could do polynomial division. If we get no remainder, there's no errors. If we get a remainder, there's an error. Maybe. Or actually, if we get no remainders, there's no error, probably. If we get a remainder, there's definitely an error. So where does this go wrong? Right? Like where do we not catch errors? We're gonna miss errors if this sum that we've got here is also happens to be divisible by G of X. If whatever remainder we had whatever error we had produced a remainder that happened to be divisible by G of X, we'll miss that error. So we could select the G of X that's not divisible by like a lot of things, right? Like common types of errors you might see, and this is what most hardware actually does. But that's not fun. Let's not do that. We're not cryptographers. We're going to leave the number selection up to them. So suppose we transmitted T prime of X, and so we don't really care about the case where this sum that we had, I probably should have written it on this table, on the slide, where this sum isn't divisible by G of X, because if it's not, there's an error, we've caught it, we're good, we can move on. We only really care about the case where it is divisible by G of X. So suppose we transmitted T prime of X, where T prime has some error that causes an odd number of flipped bits. Let's assume for a second, and this is sort of circular reasoning, but we'll get back to it, that our initial message has an even number of ones. Then if we flipped an odd number of bits, plugging in literally the number 1 into our polynomial T prime is going to give us 1, right? Because if we flipped an odd number of bits, initially we had an even number of bits. We're gonna have X to the, we're gonna have 1 to the n plus 1 to the whatever plus 1 to the whatever, an odd number of times, it's gonna be odd. We're gonna get 1. So as long as G of 1 is 0, this case will be fine, right? We'll detect any number of odd bit flips, just like a parity check bit does. And if we pick G of X equal to X to the I plus 1, then G of 1 will always be 0, because 1 to whatever is 1, plus 1 is going to be 0 over the integers. So this is almost as good. This is as good as a parity bit. In fact, if you pick G of X equal to X plus 1, it is just a parity bit. If you work out the math, dividing by X plus 1, shifting by, you shift by 1, you divide by X plus 1, but that doesn't actually do anything, and you add that parity bit. So this is no different than just using a parity check bit when you choose G of X equal to X plus 1. So in the worst case, we've at least got a parity check bit. We've done all this math and we've gotten ourselves a parity check bit. What else can we do? Say we had a sequence of errors in a row, right? then we could take the message we meant to send, subtract the message we actually did send, and this will give us E of X, which is just, think of it as like a number where every single bit that has an error is like set to 1, right? G of X divides T of X, because that's how we constructed T of X. So, oops, that should be E of X. So if, okay, that should be an E in there somewhere. So G of X divides T of X. If G of X divides T of X, that means for it to divide E of X, it should also divide T prime of X, right? And the case we care about again is the case where it does, like everything does divide, even though there's an error. Because if it doesn't divide properly, then we'll detect an error and we won't, it won't be a problem. So this should say E of X. If G of X doesn't divide E of X, that means it doesn't divide. Let's say it does. It goes both ways. Does that make sense? If it divides the sum of the two things, it divides one of them, doesn't divide the other, then it won't divide the whole thing. So what does E of X look like if we had a sequence of errors? E of X is going to be, because E of X is just the number of bits where we had errors, it's going to be something like x to the n plus x to the n1 plus x to the n2 x to the nk, where each number is like a decreasing sequence, right? It'll be like x to the 4th plus x to the 2nd plus x to the 1st. We had 3 bits that were flipped sort of in a row. So we can factor out E of X. We can pull out the largest polynomial NR, and we're left with x to the n1 minus NR, x to the n2 minus NR, so on and so forth. G of X, which we've picked as x to the I plus 1, can't divide x to the NR, right? Like that's just not going to divide cleanly because that's got a plus 1. It doesn't. So the only case where our CRC fails is if this divides, if x to the I plus 1 divides this sum. How can we prevent that? How can we make sure that two polynomials never divide each other? Or say you were working in integers and you had the number like 7. How do you make sure that whatever you pick won't divide 7? Or say you had just like some number of errors that you wanted to prevent. One way of doing that is to just make sure the degree is larger than the number of errors you want, right? If we had a polynomial of like x to the 20 and we had 15 errors, this thing in here had a max degree of like 15. We're not, x to the 20 is not going to divide into x to the 15. This won't divide out. It'll give us a remainder. So that's sort of how CRC works. Just to like go back. Just to go back a little bit. We pick the bits that are flipped. We look at what they look like, right? They're going to be a sum of different elements, all of which are increasing like this. And then we ensure that if we pick the right type of generator, it's not going to divide this. So G of X, when we do our CRC division, when we do this, we've got this term and we divide by G of X, even though there's an error in it, it's not going to divide cleanly. And so we'll know that an error happened, no matter how many errors happen, as long as it's less than the degree of the polynomial and they're all next to each other, which is how errors happen in the network. So the Hamming distance of this code that we've talked about is still 3, I want to say, right? So technically, we can only detect 1-bit errors if we were, we cared about errors that happen randomly. But if we care about errors that happen in chunks, the polynomial division map works out really nicely. G of X with a large enough degree can divide that. So specifically, the degree of G of X is how many errors, first errors, it can detect. Okay. But dividing polynomials is not fun. I don't want to do it. But the computer is more than happy to do it. Because if you look at the synthetic division algorithm, all it is it's, especially over C2, you're just shifting bits and XORing stuff together. And the computer loves doing that. So it's fast at detecting and correcting errors of size 1. It's just as good as Hamming codes in that sense. But its true power shines because it can detect any number of burst errors, depending on the generator polynomial that you choose, and you can choose whatever polynomial you want. CRC is used in literally every single device on the planet. When you send something over the network, you can take 438 if you actually want to learn about this. The computer hashes everything with CRC. It puts these checks and bits with CRC, And then the receiver checks those, and if those don't line up, it asks for a request again. This happens all the time, millions of times per nanosecond, millisecond, whatever, whenever your computer is sending messages. Sometime soon, next week, or no, we'll discuss more advanced codes that show up in things that we interact with as people, not just necessarily the computer, specifically barcodes and QR codes, which are Reed-Solomon codes. And these are, I think, the most famous type of code just because they're better than Hamming codes. They're better than, they're easy to, they're just ideal. Is that next week? 2 weeks?
After.
After Thanksgiving break, 2 weeks.